Welcome to Part 3 in the module on Patterns and Frameworks for Concurrency and Synchronization. In previous parts of this module, we started by describing the active object pattern, and then we talked about the ACE Task framework, which can be used to implement this and other concurrency patterns. Now, we're going to explore yet another path through our pattern language for JAWS to illustrate how we can apply the ACE Task and Acceptor-Connector frameworks in the context of a web server. This path will be our first true multi-threaded path through the design. We'll come back and explore a number of different multi-threaded paths in later parts of this module. So this particular example actually builds quite nicely on our previous version that we showed with Acceptor-Connector, which itself built nicely on top of the reactor. And we're going to add just a few very minor tweaks in order to be able to get a new and more powerful concurrent multi-threaded design. In particular, we're going to start first by showing how we can use the ACE service handler, which inherits from ACE Task, in order to be able to spawn off separate threads, one per connection, and use them to service the incoming requests concurrently. So to do this, we're going to define a class called TPC, for Thread Per Connection, HTTP Handler. And of course, this class will inherit from ACE Service Handler, and it'll use ACE sock stream, so it'll be able to send and receive via the socket wrappers we talked about before. And then it's going to have a hook method that'll get called back by the ACE Acceptor framework to activate this particular object when it's been connected and created. And unlike before, where the activation operation simply registered the object back with the reactor for a purely reactive solution, this time when this happens, we're going to go ahead and activate the object to run in a new thread of control. As we saw before, the activate method under the hood will spawn a thread and then pass in the service run adapter function that's part of the ACE Task framework, and that will end up calling the service hook method on TPC HTTP handler. Here's the service method. Keep in mind this method is now running in its own thread of control. And it does pretty much exactly what we've always been doing. It turns around and extracts out the GET request from the input stream that we got from the client. It memory maps that GET request URI, finding the appropriate content in the file system. And then we turn around and use a send operation to send all the N bytes back to the client in one transmission operation. So this particular approach runs very efficiently. It runs in a separate thread of control. And therefore, if for any reason we have blocking because of flow control, other threads will not be perturbed. Here now we illustrate how we can go ahead and extend the ACE Acceptor in order to provide the next piece of this particular solution. So we're going to implement something called a TPC Acceptor. And this is going to be an acceptor for HTTP objects, and TPC, of course, stands for Thread Per Connection. Here's the illustration of how to do this. We go ahead and we instantiate the template, the ACE Acceptor template, to make a TPC HTTP Acceptor object class. And this, of course, we instantiate with the TPC HTTP handler that we just looked at, and the ACE sock acceptor. So we've got all those pieces set up. Now we go ahead and reuse our reactor HTTP server from our earlier Acceptor-Connector example to make our HTTP server daemon. And then using this, we create a main thread of control where we've got, for the whole function, for the whole program, we make ourselves an ACE reactor. We go ahead and create an instance dynamically allocated of HTTP server daemon. And we allocate this dynamically so that it gets cleaned up properly by the reactor when things shut down. And then we go ahead and run the reactor's event loop. And henceforth, everything is driven by callbacks. And the neat part about this is, as we'll see, there's really nothing much different from our original solution, except now each incoming request is handled in its own thread of control using a thread per connection approach. With HTTP 1.0, each request is a connection. That's a little different with HTTP 1.1, where you can actually send multiple requests on a given connection. Note the extensive reuse of the design and the code in this example. It looks very much like what we looked at before. I didn't choose to illustrate the use of the service configurator framework that we talked about before, but I could have. That would have been another thing we could have done to have dynamically linked these capabilities into the address space of the program when it started to run or at runtime. So to summarize this particular section, only very minor changes were required to our design and to our implementation in order to go from a reactive approach to the active object approach using thread per connection. And it just went from this model we had here, where you had a reactive callback driven approach using the handle input methods, to an approach using an active object, where we were able to create the TPC HTTP handler that could run in its own thread of control. The reason why there's so few changes required is because of the fact that we have designed the ACE frameworks using a very carefully thought out variation-oriented design method. And what that meant is we spent quite a long time looking for sources of commonality and variability. And every place where we found something that could vary, for example, single-threaded to multi-threaded, we would find a way to make that variation as easy to extend and add as possible, with as few changes to the design, to the architecture, even to the implementation. And so that's why we're able to make these changes quite cleanly without having to perturb the rest of the architecture and the rest of the design. This is something that typically occurs with experience. It occurs with the opportunity to refactor your software and continually improve and evolve it. As before, very little code was required to do anything related to the application processing. We've seen the same application logic repeatedly now, and the frameworks, now multiple frameworks from ACE, the Reactor, Acceptor-Connector, and ACE Task, took care of the event handling, connection establishment, service initialization, concurrency, and so on. Like I said, we didn't do the service configuration part, but we easily could have, and it all would have fit together nicely in a common model. So the generic framework factors out all this code in a common way, and we just have to worry about programming variability, which also is expressed in a common way as well. There's still a role for the reactor pattern, by the way. It's important to note that we haven't completely gone back and erased all the earlier parts of our design. We just moved the reactor pattern out of the critical performance-sensitive path through the code. It works quite nicely when used as a way to handle various kinds of events, such as accept events. And we moved it out of the way so that the actual data processing now takes place in separate threads of control.